In this problem, I want to actually combine two problems together. So we're going to do what we just did for benzene and tetrachloromethane for calcium chloride in water. And then we're going to look at some numeric values that go with it for our enthalpy of solution. So here we're trying to combine calcium chloride and water and decide if this is going to be exothermic, endothermic, or an ideal solution that forms. So what we're going to be bringing together is our calcium chloride and our water. Now, our calcium chloride is an ionic compound, so it doesn't actually have as many intermolecular forces because we have ionic bonds that are in between these ions. We have a calcium that's a +2 charge, and our chlorines are each -1 charge. So that +2 charge is significant. I mean, it's a pretty big magnitude compared to +1 at least. So what we'll have here is London dispersion. And we're then going to have ion-ion interactions, which are just ionic bonds, right? So we'll have ion-ion. Now looking at our water, this is a polar molecule with hydrogen bonds. So we'll have London dispersion. We'll have dipole-dipole interactions. And we'll have hydrogen bonding. And these are for our solute-solute interactions. I'm sorry, our solvent-solvent for our water and our solute-solute for calcium chloride. So what happens when we bring these two together? Well, when we bring them together, we create some solute-solvent interactions. So we still have our London dispersion forces. That doesn't change, at least. But we don't have dipole-dipole interactions. Our ions that are full charges don't have a dipole moment to them, so we won't have a dipole-dipole interaction. We also don't have a hydrogen bonding interaction that's occurring with the new compound. We have lone pairs on the chlorine ions, I guess, so like there is that component of it, but there isn't a distribution of charge that's different. So I think then what would capture that interaction between the chloride ion and the water better than a hydrogen bonding interaction would actually be an ion dipole interaction, which is stronger, right? So we'll have ion dipole interactions. And for each ion, it'll have 6 of these. And there'll be 6 water molecules that can surround it. And so that's what we'll have for our interactions together. So now comes kind of the difficult part of evaluating, well, am I going to put more energy into breaking this, or am I going to get more energy out from forming this solution? And it's kind of one of these comparative studies where you're weighing your different options. So like when we look at our calcium chloride, for instance, we have these ion-ion interactions that are breaking apart. And they're being replaced with ion dipole interactions. And so the ion-ion interaction is stronger. That's true, but we might not have as many. There might be 4 versus the 6. So I think overall, when we go from our ion-ion to our ion dipole, we're going from a stronger to a weaker interaction. But we might be forming more ion dipole interactions. So it's kind of a balance. Then when we look at water, we are losing our dipole-dipole interactions and our hydrogen bonding interactions, but we're gaining a stronger interaction. That ion dipole interaction is significantly stronger than a hydrogen bonding interaction. And so we're definitely going to have more or stronger IMFs going from water to the water solute solution. And so then you have to ask yourself, well, which of these is going to be stronger? Like what's going to be what's going to tip the scale to endothermic versus exothermic, right? And honestly, at this point, you can make an argument either way. It might be how much of our calcium chloride, that +2 charge is significant. That forms a strong interaction with those -1 ions. And so these are all the kinds of questions that you can have, and you can build an argument and support it with the evidence of the intermolecular forces and your prioritization as you see it between them. But at the end of the day, looking at something like this, I'm like, I mean, I see an argument for exothermic and I see an argument for endothermic, and it kind of leaves a question. So let's look then at the actual numbers for this and see what it is. Okay, so continuing what we've been talking about with our calcium chloride and our water, we can now get a little bit more information and try to actually calculate if this is going to be exothermic or endothermic. So I've got a bit of information here. So the enthalpy of solute for calcium chloride is going to be 2,255 kilojoules per mole. And just looking up in tables and trying to learn more about this reaction or this solution formation, I found that the enthalpy of hydration is negative 2,378 kilojoules per mole. And so the question is really, what is that enthalpy of solution? Now, enthalpy of hydration is a new word, right? So enthalpy of hydration is going to be the sum of the enthalpy of solvent and the mixing enthalpy when the solvent is water. Like, why did we have to combine these? Why can't we keep it all separate? And so let me write that out as an equation, that enthalpy of hydration equals the enthalpy of the solvent. So that's breaking those water-water interactions plus the enthalpy of mixing. And so it's just taking two of these enthalpies and combining them for for hydration, to make hydration. So we can take our equation that the enthalpy of the solution is going to be equal to our enthalpy of our solute plus the enthalpy of our solvent plus the enthalpy of mixing. And we can change it to just the enthalpy of solute plus the enthalpy of hydration. And this only works when water is the solvent. So now we have some values we can plug in here, right? So we've been told the solute enthalpy is 2,255 kilojoules per mole. It's a positive number, which is great. It should take energy to break the interactions between the calcium and the chlorine. So this will be 2,255. Plus then the enthalpy of hydration, which is a negative value. Now, just seeing that that's a negative value tells me that my enthalpy of mixing is significantly higher than my enthalpy of solvent, which it should be. The question is that enthalpy of mixing larger than the enthalpy of my solvent plus the enthalpy of my solute? That is what tells me if it's endothermic or exothermic. So this is going to be negative 2,378 kilojoules per mole. All right. So with that, then I'm just adding these together and I get a value that's negative 123 kilojoules per mole. So that negative value right here, we'll just highlight this whole thing, that tells me that this is exothermic. So going back to our the work we did previously, if it's exothermic, if it's releasing energy, if it means it's forming stronger interactions in the solution than it did in our pure substances, it means that the IMFs that are created for the water molecule interacting with that ion are significantly stronger than just the water interacting with the water. And that overpowers any loss of forces that are felt for the ions that were in an ion-ion interaction and move to an ion dipole interaction. It also means this will feel hot to the touch.